In the previous video, we learned that if we determine the gradient of the velocity time graph, the gradient that we get will be equal to the value of acceleration, and we can plot this value of acceleration in the acceleration time graph. Now, are we able to turn this around? Means by are we able to find something in the acceleration time graph which is equal to the value of the velocity, and we can use that value to be plotted on the velocity time graph? And answer is yes. And the principle that we use here will be quite similar to the way we get from velocity time graph to displacement time graph. Okay, so if we take the area under the AT graph from T0 to T1, let's say I pick my T0 to be at time equal to 0, my T1 to be at time equals to 2. If I find the area under the graph, the AT graph, over this specific time period, the area will be equals to the change in velocity during time 1 to time 2. Means by what is the change of velocity from this starting time until this end time. So if you take the final velocity minus the initial velocity, the answer will be equals to the area under the graph for that time period as well. Okay, let's straight jump into an example. Let's do it for the first section first. For the first section, you can see that the area here can be calculated by taking AX and AX, which is 1.5, multiplied by the span of 2 seconds. So 1.5 times 2 is 3. What about the unit? Meter per second square times second. So it becomes meter per second. So 3 meter per second. So you know that this is definitely related to speed. Okay, so 3 meter per second, and I say this 3 meter per second here will be equals to the change in velocity during time 0 to time 1. Let's check whether it's true or not. So the final velocity at time at the final moment is 3, and the initial velocity at time equals to 0 is 0. So 3 minus 0 is just 3 meter per second. So we prove that it's true. Let's move on to the next section. Next section, we can see that the area under the AT graph is 0 because the line is straight on the time axis. So no area to find here. So if you have no area, then that means there's no change in velocity. And as we expect, the velocity is not changing across this time span of time equals to 2 to time equals to 6. The velocity remains constant. Okay, third section. We can find our area over here. We are combining these two sections to do together. So if you find the area over here, you will get 10 minus 6, which is 4 seconds, multiplied by negative 1.5. So you get negative 6 meter per second. Okay, any area which is below the time axis will be a negative area. And since the answer is negative 6 meter per second, you should expect the velocity to change by negative 6 meter per second. So let's look at it. The final velocity, which is at time equals to 10, is negative 3. Okay, the initial velocity when time is equal to 6 is 3. So you take negative 3 minus 3, you get negative 6. Okay, final minus initial, negative 3 minus 3, you get negative 6 meter per second, which is again the same as the area under the graph that we determined. Okay, the next section from time equals to 10 equals from time equals to 10 to time equals to 14. Over this period of time, you can see that there's no area to be found here. So you expect there's no change in velocity during that period as well. Okay, for the last section, you can see that for the acceleration time graph, the area can be found by taking 1.5 multiplied by 60 minus 14, which is 2. So the answer you get will be 3 meter per second. So again, you expect final velocity 0 minus initial velocity negative 3, you should get 3. And yes, the answer is 3 meter per second, just like the area under the graph that you determined here. Okay, so this whole analysis here proved that the area under the AT graph for a certain time period will be equal to the change in velocity that happened during that period of time as well. Okay, So if you would like to summarize everything in a relationship similar to this one, to get from velocity time graph to acceleration time graph, we can determine the gradient. So the gradient of the velocity time graph will be equivalent to the value of acceleration, which we can plot in the acceleration time graph. But to get from the acceleration time graph to obtain something about the velocity, if you are able to determine the area under the graph of the acceleration time graph, and you are able to determine the change of velocity. Okay, but if you also know the initial velocity, then by knowing the area under the graph, you know the change. So you know the initial, you know the change, you are able to determine the final velocity. So if you know both, you are able to determine the final velocity. Okay, so this is related to gradient, which is related to differentiation. Area under the graph will be related to integration. So integration, if you remember from your maths, that's a plus c, right? The constant. And that constant is actually the initial velocity. But let's not go too deep about this. Okay, so that's all, and this will be the last video that wraps up everything about motion graph.